For stationary state, we can prove that the probability density function is independent of time. How do we do that? What's the probability density function? It's psi star psi, right? So what would that be? This is your probability density function. That's psi, little psi times f star times little psi times f. What would that be? This is little psi star f star little psi f. And these are all just multiplications, so I can rearrange. Right? So I can say this is psi star times psi times f star times f. Right? So what is f star? This one is what? F is e to the negative I e t over h bar. So what is f star? Take the complex conjugate, you see an I replaced by negative I. So in this case, you're going to have e to the negative of negative I. So that's plus I e t over h bar. So this is really like e to the x times e to the negative x. What would that be equal to? E to the 0, which is just 1. So this one will just be equal to 1. So what we're saying is big psi star times big psi is just equal to little psi star times little psi. So it's independent of time. Okay? So that's why it's called a stationary state, because the probability density is independent of time. Psi itself does depend on time. Big psi depends on time, this depends on time. But it's equal to this, okay, which is independent of time. It only depends on the coordinates of your particle. Alright, so let's look at an example here. Let's say h psi of n, so you have a series of solutions, psi 0, psi 1, psi 2, and so on. Let's say that's your eigenbasis for your Hamiltonian operator. Okay, so h hat operating on that gives you n squared beta times psi n. So these are your eigenvalues, right? The constant that you get is your energy. So let's call that E sub n. And so let's say psi, big psi, happens to be little psi 3 times e to the negative I e3 t over h bar. Okay? What would be the allowed energies for the system? What is E0? 0. What is E1? 1 squared beta. So that's going to be beta. What is E2? 2 squared beta. So that's 4 beta, right? What is E3? 3 squared beta, which is 9 beta, and so on and so forth. So, if we were to try to measure the energy of this system, what is the probability that we're going to get 4 beta? You remember from our earlier postulates? What is our psi in general? C0 psi 0 plus C1 psi 1 plus C2 psi 2 plus and so on and so forth, right? So what's the probability that if you measure the energy, you get 4 beta? Then that's just going to be C sub 4. What's 4 beta? For n equals 2, right? For psi 2. So then the probability that you're going to get the eigenvalue of psi 2 would be C2, absolute value of C2 squared, right? What's the absolute value of C2 squared? Okay, here's C0 psi 0, psi 1, psi 2. What's our psi? You're given that psi is C3 is 1 times psi 3, right? So C0 here is, according to this, 0. C1 is 0. C2 is 0, C3 is 1, C4 is 0, and so on. So what is the probability? It's you were given that psi is just equal to psi 3. So the probability of anything besides the energy E3 is 0. Okay? What's the probability that you're going to get 9 beta? Well, 9 beta is the energy of corresponding to psi 3, so the probability of getting 9 beta is 1. Absolute value of C3 squared, so that's just going to be 1 squared. In other words, that's basically what we said. If psi is an eigenfunction of the Hamiltonian operator, it has a well-defined energy. In this case, what's the well-defined energy? 9 beta. Okay? Because we said psi in this case, and this is suppose. This one says suppose, okay, that psi is equal to psi 3. This is psi 3. Okay, true or false? A system in a stationary state has a well-defined energy. That's true, okay? In fact, H hat psi would be equal to E psi. E is well-defined, okay? If it's in a stationary state, it is an eigenfunction of the Hamiltonian operator. Show that any linear combination of degenerate stationary states is also a solution to the time-independent Schrodinger equation. What's our time-independent Schrodinger equation? H hat psi equals E psi, right? So let's say our psi, suppose our psi is equal to C psi psi 1. Let's say psi 1, psi 2. Let me write my psi correctly. Psi 1, psi 2, and so on are the stationary states. Okay, so let this be your stationary states. Then C1 psi 1 plus C2 psi 2 and so on would be a linear combination of your stationary states, right? So what are we trying to prove here? Is psi H hat psi equal to E psi if psi is a linear combination of stationary states? Let's see. H hat, let's just do a linear combination of these two, right? So C1 psi 1 plus C2 psi 2 equals, well, Hamiltonian operator is a linear operator. I can distribute, and I can pull out constants, right? So this is going to be C1 H hat psi 1 plus C2 H hat psi 2. Okay? Well, what is H hat psi 1? That's E1 psi 1. And what is H hat psi 2? E2 psi 2. Is that equal to a constant times the original psi? That's my original psi. My original psi is C1 psi 1 plus C2 psi 2. Can I pull out the constant there? What would be my constant? Only if E1 is equal to E2, right? I can't pull out a constant here. That's why we have to have degenerate. So if we say that if E1 is equal to E2, then this is going to be E1 or E2. Then you say your wave function, okay, the state function is an eigenfunction of the Hamiltonian operator if it's a linear combination of degenerate stationary states. If it's non-degenerate stationary states, you take the linear combination, then you end up with a psi that is not a stationary state. It's a psi that is not an eigenfunction. So that psi, okay, if E1 and E2 right here are not the same, then you cannot write this as a function of coordinates times a function of time, the overall psi. So we say in this particular case, if E1 is not equal to E2, then your psi is not an eigenfunction of the Hamiltonian operator. You cannot write it as a function of coordinates times a function of time. But this linear combination is still a solution of the time-dependent Schrodinger equation. We're looking here at the time-independent. Okay, and this is our next thing to prove here. Any linear combination of stationary states, whether they are degenerate or not, okay, is also a solution to the time-dependent Schrodinger equation. So what was our time-dependent Schrodinger equation? IH bar, partial derivative of psi with respect to time, is equal to H hat psi. Right? So this is provided your H Hamiltonian doesn't depend on time, right? So let's do this. IH bar, derivative with respect to time. Let's just do linear combination of two. So C1 psi 1 plus C2 psi 2. What do we get? IH bar 1. C1 derivative of psi 1 with respect to time, right? That one. And then that one. Plus C2 derivative of psi 2 with respect to time. Okay? And I'm going to go ahead and multiply the constant there. So this is going to be C1 IH bar derivative of psi 1 with respect to time plus C2 IH bar derivative of psi 2 with respect to time, right? But what is this? C1, this is just H hat psi 1, right? Plus C2 H hat psi 2. Okay? Since the Hamiltonian operator is a linear operator, I can move back my constants in. So I can say this is H hat C1 big psi 1 plus H hat big C2 C2 times big psi 2. And since it's a linear operator, that's the same thing as H hat of C1 psi 1 plus C2 psi 2. Okay? Which is the same thing as H hat psi. And so what we've shown is this thing on the left, IH hat d psi dt is equal to H psi. So what we have shown is IH bar derivative of psi with respect to time is equal to. So any linear combination, they don't need to be degenerate. They will still be a solution to the time-dependent Schrodinger equation. It just so happens that if that linear combination involves non-degenerate states, non-degenerate stationary states, then it will not have a well-defined energy. Okay? If you make a measurement, there's a probability you might get the energy corresponding to psi 1, or there's a finite probability that you might get the energy corresponding to psi 2, and so on. Okay? So let's say H hat psi sub m, look, this is little psi, right? It's m squared b times little psi, where m is 0, plus or minus 1, plus or minus 2, and so on. What if we took the linear combination of psi 3 and psi negative 3? Would that still be a solution to the time-independent Schrodinger equation? You're supposed to show that it is, so why should it still be a solution to the time-independent Schrodinger equation? What is E3? That's 3 squared b, which is 9b, right? What is E for negative psi negative 3? It's still negative 3 squared b, so that's 9b. So psi 3 and psi negative 3 are degenerate states. So a linear combination of degenerate states will still be a stationary. Degenerate stationary states, a linear combination of degenerate stationary states is also a stationary state. So let's make this your homework. Okay? So prove that it is a solution to the time-dependent and the time-independent Schrodinger equation. This specific case. Okay?
Don't change it yet, please.
Huh?
Don't change it yet, please. I just want to take up the last one.
I'm sorry?
I just want to write that right quick.
Okay. Oh, that's just linear combination. So you have C1 psi 3. So that's C3 psi 3 plus C sub negative 3 psi sub negative 3. Those are just your coefficients. So your coefficient here is 2. Your coefficient here is 1. So, in fact, that's not going to be normalized, right? What should be the normalized coefficients? 2 squared plus 1 squared is 5. So it should really be 2 over square root of 5 and 1 over square root of 5. Okay, so there should be a normalization constant there. But it doesn't matter if you put that extra constant there in terms of the proof. Okay? Because it could be any linear combination. It just so happens that in this case your linear combination is not going to be normalized. Okay? So it's your homework. And this is more of the same, except that in this case, okay, it is a linear combination of non-degenerate states, right? What is E3? 9b. What is E4? 16b. So the linear combinations, this is C3 psi 3 plus C4 psi 4, right? This linear combination is a linear combination of non-degenerate states. Therefore, it will not be a solution to the time-independent Schrodinger equation, but it will still be a solution to the time-dependent Schrodinger equation. Okay?